So, this is in continuation of our previous talk. Here we will discuss the limit of sequence of a real numbers with few examples, and we will also discuss the monotonic sequence and oscillatory sequences. Now, we will discuss the limits of sequences. This pen is not good. Limit of sequences. Okay. Suppose A n be a sequence. We say the sequence A n is the limit. Let A n be a sequence of real number. I am just saying now real number. Okay. I am not now taking any rational or something. Real numbers. Yes. Huh?
Sir, I think from the previous film was perhaps better.
Better.
Picture is better.
Okay. 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 Let A n be a sequence of real numbers. Suppose we say limit of the A n as n tends to infinity is say L, means for a given epsilon greater than 0, for a given epsilon greater than 0, there exists a positive integer n naught such that the difference between A n minus L, this difference can be made less than epsilon for all n when n is greater than n naught. Okay. The meaning of this is very clear. Suppose we have this number L and there are the sequences A 1, A 2, A n and so on. We say this sequence converges to L. It means that if we find out the distance from each L, from each term, distance of each term from L, then this distance keep on reducing and reduce it to 0, then we say the sequence A n converges to L. Basically, this mode is the distance. This mode means the absolute difference between the two values. Now, A n and L both are real numbers. They can be represented by means of a point on the real on the axis. So, once you have the point, you can identify the distance, and this is the distance A n minus L. Why absolute value? Because there may be a sequence which may converge from this side, it may go from left hand side. So, L may be less than this, L may be greater than this. So, but in absolute value, the distance must tends to 0 as n tends. So, we say the sequence is said to be convergent when the difference between A n minus L, or the distance of A n from L keep on reducing and reduce to 0. So, this is the way we can. Now, this has been generalized to an arbitrary metric space, because this is the case when we are dealing with the real numbers only or complex numbers. Then once you have the real or complex number, the distance notion is simply the absolute value, isn't it? The absolute difference between the 2 points is the distance of the two real number or distance between the two complex number. But suppose x is an arbitrary set of points, then the notion of the distance will be defined in such a way, so that the axioms of the usual notation must retain. Okay. That is this. So, that we will take in fact in an arbitrary space, in an arbitrary set of points x, okay, which has the notion of the distance by d, notion of distance given by d, okay, given by d, we say a sequence A n converges to L under D if for a given epsilon greater than 0, there exists an n naught such that the distance between a n comma L is less than epsilon for all n greater than equal to n naught. This is a general way, but we are not dealing with the general, that is why I restricted only mode. But what is the distance function? Distance means that a distance d, a function d is a mapping. What is the metric or distance function? This is non-negative, it always be greater than equal to 0 and 0 when a the 2 points are coincident. Okay. Then we get the reverse, if a n and L is position reverse, we get the same value, and then the triangular inequality. So, these conditions are satisfied, then we. So, we are not there, that is why we will drop this one and we will simply take up the mod sign just to say. Okay. Because here in fact, I wanted to introduce that metric distance, but because it is early, so that is why it is not. Okay. So, we will take this. Now, divergence sequences. Divergence sequence. We define the divergence sequence n is said to be diverging. A sequence a is said to tend plus infinity, is said to plus infinity if corresponding to a positive number, if corresponding to a positive number a however large, a number, an integer n naught, an integer n naught greater than 0 can be found, can be determined such that n's are greater than a for whenever n is greater than n naught. We say the sequence n tends to plus infinity. So, these are the sequence a 1, a 2, a n and so on, and this tends to plus infinity. It means, the limit of this sequence a n is not finite, it is infinite. So, it is a diverging sequence. A sequence is said to be diverging when the limit of the sequence does not exist. Either it will be a plus infinity or minus infinity, then it is said to be a diverging sequence. Okay. So, when you say it is a sequence a n goes to plus infinity, means that whatever the number you choose, you can always find an integer n naught such that the value of the coordinate of this sequence will exceed by that number. Suppose I would say a is equal to 10 to the power 10 to the power 10, then this number is there, say 10 to the power 10 to the power 10 like this. Then one can identify a number n naught here, that all the terms of the sequence after this will greater than this number. So, we say it is tending to plus infinity. Similarly, we say a sequence a n, similarly sequence tends to minus infinity if corresponding to a large positive number a, large positive number A, n naught can be determined, n naught can be determined such that a n's are less than minus a for all n greater than equal to n naught. Then it is tending to minus infinity. Okay. So, a sequence which is either so a sequence a n for which either the limit of a n as n tends to infinity is plus infinity or minus infinity, limit of this tends to plus infinity or minus infinity is it not, plus infinity or minus infinity is said to be a diverging sequence. Of real numbers, okay, of real numbers. Okay. For examples are, suppose I take a n, the sequence say n square, this will diverge. Okay. Similarly, other sequences also you can say it will diverge to plus infinity. If I take a n equivalent to say minus n, it will diverge to minus infinity, like this and so on. Okay. Then oscillating sequence, oscillating sequence. A sequence a n of real numbers is said to be oscillatory if the limit of a n as n tends to infinity does not exist, and limit of this neither does not exist or neither tends to a finite value, neither tends to a finite value or nor or plus infinity or minus, nor plus infinity or minus infinity, plus infinity or minus. The meaning is that a n is such where the limit does not exist. Limit does not exist means that is limit of the sequence a n when n tends to infinity does not exist. Because when we say the limit exists, it means whatever the path you choose, because where the definition of the limit, when the limit is there, this is the definition of the limit, that if the limit exists means this is less than. So, whatever the path you choose, the limit of a n minus l can be made as small as we please. The difference between a and l should be made as smaller in this as one can desire. There should not be fluctuation, but if such a sequence are there where this difference cannot be made as smaller, sometimes it is small, sometimes it becomes very large, then in that case the limit does not exist, or along different subsequences it has different values, then the limit does not exist. For example, if suppose I take a n to be minus 1 to the power n, then along the positive path it will go to 1 if n is even, that is when the sequence are chosen like this a2, a4 etc., the limit will go to 1. But if the sequence is chosen to be odd, then n is odd, that is a 1, a 3, this limit will go to minus 1. So, the sequence when n tends to infinity does not tends to a one value, because it fluctuates like this. Here this minus 1, here is plus 1. So, what happen is a n you cannot find any. Suppose I take 1 is the value, then a n minus 1 cannot be made epsilon, because as soon as a n odd becomes, then it will be minus 1, minus 1, minus 2. So, it becomes very large. Similarly, so it does not go to that, does not have a finite value limit. Similarly, if we take the sequence minus 1 to the power n, say this one, then what happens when n is sufficiently large, when even number, it will go to plus infinity. It goes to plus infinity if n is even, and goes to minus infinity if n is odd. So, it does not have the limit. Okay. Similarly, however, the sequence a n which is minus 1 to the power n by n is not an oscillating series, is not is not a sequence, sorry, is not an oscillating sequence. Why? Oscillating sequence are those sequence whose limit does not exist. The limit is not tending to a finite value, or plus infinity or minus infinity. Now, this sequence tends to value 0, though it is alternately positive negative, but what happens if this is the value 0, you are getting minus 1 by n, plus 1 by n, then as n increases, you are taking minus 2 by n, plus 1 by 2 n, like this. So, this goes to here, this goes to here. So, after a certain state, the difference between a n minus 0 can be made as small as we please, is it not? So, that is why this sequence is a convergent sequence, converges to 0. So, it is not a 0, but convergent. Okay? This is convergence. Then bounded sequence. So, we say here also we can characterize the oscillating sequence of finitely oscillating and infinite. Finitely oscillating sequence, when the limit tends to does not tends to finite value, but does not go to plus infinity, minus infinity, but it alternates. And infinite means that is when we are unable to get, that is a sequence is said to be a finitely oscillating. No remark, a sequence, an oscillating sequence a n is said to be finitely oscillating if there exists a number a, if it is possible to find a number a greater than 0, such that all the terms of the sequence remain less than a. All the terms of the sequence remain less than a for all values of n. We are able to get it just like this series. This sequence is a finitely oscillating, because a number 1 can be obtained such that mod of this a, but this is not a, because it does not even a you cannot find. Otherwise infinite oscillatory. Sequence. Okay. So, we can characterize these two into two. Okay. Bounded sequence we have already discussed. So, no point of view bounded sequence, and then every convergent sequence is bounded. A sequence a n is said to be bounded. A sequence a n of real numbers is said to be bounded if there exists k and capital K such that a n is greater than equal to small k, greater than equal to is less than equal to capital K. Suppose we have the two bond. It is not necessary that we have the same bond. Okay. So, a sequence A n is said to be bounded below if there is a small k such that all the terms of the sequence are greater than equal to k, then this will give the bounded below, while this thing will give bounded above. Okay, bounded above. And if we combine both these and let capital A be the maximum of k and capital K. Okay. In fact, this is capital K only. Okay. Then in that case, mod of A n is less than equal to k. Then we say this sequence is bounded. Okay. Bounded. So, lower bounded, above bounded and bounded, or like this. Okay. So, we get this one, and every convergence sequence is a bounded sequence, that we have seen in the. So, result is every convergent sequence is a bounded sequence, is bounded. I think this proof we have done is. What about the converse? Can you say every bounded sequence is convergent? The answer is no, but converse is not true. However, converse need not be true, because if you take the, for example, if you take the sequence A n minus 1 to the power n, this is a bounded sequence, but not convergent. Okay. So, we can get this clear. Now, fundamental theorems of this limit is the same as this. So, we are not touching those things. Okay. Let us see the results, which is very important result. There is one result which is known as the sandwich theorem. What the result says is, if sequence A n, B n and sequence C n, let A n, B n and C n be all the sequences such that of real numbers, such that all the sequences of real numbers such that A n are less than B n less than C n. Okay. Suppose we have this sequence, and this is true for all values of n. That is, 3 sequences are given and they satisfy these inequalities for all n, and limit of A n as n tends to infinity is the same as the limit of C n as n tends to infinity, and suppose it is L. Then what this result says, then the limit of this sequence B n will also be L. This is known as the sandwich theorem, that if you want to find the limit of the sequence B n, if we are able to identify the lower and the upper bounds for each n, that is A n sequences where the corresponding terms are satisfying this condition, and if this left hand sequence and right hand sequence converges to the same limit, then the middle sequence will also converge to the same sequence. Okay. Okay. The proof is very simple. Proof is not that, because proof is why it is so, because A n is given to be L. Okay. So, since limit of this A n is L, so it implies that A n must lie between L minus epsilon L and L plus epsilon L for n greater than equal to n 1. Similarly, limit of this B n is L. So, this implies that L minus say same epsilon we can choose or different also
The limit of Cn.
Cn, sorry, limit of Cn. So, L minus epsilon less than Cn less than L plus epsilon after integer n greater than equal to n 2. Now, if I picked up the n greater than n 1 and n 2, choose n naught as the maximum of n 1 and n 2. So, for all n greater than n naught this condition is satisfied, for all n greater than n 2 this condition will satisfy. Okay. So, we get from here a n and b n lying. So, b n is the number lying between a n and c n. So, we can say L minus epsilon is less than b n at the most equal to less than L plus epsilon for all n greater than n naught. Is it not clear? So, as n tends to infinity, limit of the b n will go to n. So, this okay. Now, this is used to find the limit of the complicated expression. For example, what is the use? Suppose I take this problem, prove that limit of this as n tends to infinity 1 by n square, 1 by n plus 1 whole square and so on, 1 by 2 n square is 0. Limit of this is 0. We wanted to show this part. So, we know that 1 by n square 1 plus n, the lowest term is 1 by 2 n up and largest term is this. So, which calculation shows that 1 by n square 1 over n plus 1 whole square and 1 by 2 n square. This will be less than total terms are what n plus 1 starting with n to n plus 1. So, total term is n plus 1 into 1 by 2 n square and greater than n plus 1 into 1 by n square, okay, or clearly just we get this, is it not? Now, as n tends to infinity, this is our a n's, this is our c n's. So, as n tends to infinity, because the denominator is having larger degree than the denominator. So, this will go to 0, this will go to 0. So, a n and b c n, limit of this a n is 0 is the same as the limit of c n. Therefore, limit of b n must go to 0. So, this implies limit of this b n must, this is our b n's. Okay. So, this shows the very interesting things, is it like this. Now, monotonic sequence, there are also similar types of this monotonic sequences. We have seen that there are two types of sequences which are either in non-decreasing or in, means a 1 is less than equal to a 2 less than equal to a 3 etc. These are called the non-decreasing sequence, monotone sequences. Non-decreasing, okay, it keep on in here, but maybe constant also, or a 1 greater than equal to a 3. This is called non-increasing sequence, monotone sequence. Or if we have this one, then it is called the strictly increasing monotone sequences, okay, monotonic. And if we have this one, then we say strictly decreasing. So, we get this one. Okay. Now, if these monotone sequence are there and if it is bounded above, say non-decreasing sequence which is bounded above, then it will have the limit. If it is a monotonic decreasing sequence bounded below, then it will also have a limit. So, these two results we have already discussed it, is it not? So, just I will just result. Okay. A monotonic decreasing sequence, a monotonic increasing sequence tends to either to limit or a monotonic increasing non decreasing sequence which is bounded above will be convergent. Similarly, a monotonic non increasing sequence which is bounded below will be convergent. In general, a monotonic sequence, the limit of the monotone sequence will be either finite or plus minus infinity in general, but these are the convergent criteria. So, either monotone in non decreasing or strictly increasing or strictly decreasing, that is what this also. Now, this will be used also to find the limits. Suppose for example, if we take this a n sequence as under root n plus 1 minus under root n, and I ask what is the limit of this. So, if you go to the limit as n tends to infinity, what you are getting? Infinity minus infinity, which is indeterminate. We cannot get it, but if we slightly if we manipulate it, we get divide and multiply by this. So, when you multiply by this number, then you get a x square minus a square, that becomes 1, and this is equivalent to this sequence, is it not? Now, this sequence is monotonically what? Increasing or decreasing? Decreasing, and tends to 0 as n tends to. So, limit is 0, that is what, is it not? So, we will look the some limits also which are very interesting, particularly the 2-3 limits which we get as an exercise next time. Okay. Thank you very much.